right, gentlemen. Today we're going to talk about inverse functions. The way I want you to think about these is inverse functions, similar to the idea of inverse operations, right? So, inverse operations that undo each other, like addition and subtraction, or multiplication and division. Well, functions have inverses that undo each other sometimes as well. What they do is inverse functions swap inputs and outputs. So they swap x and y. All right, we're going to use a special notation for this. And so we say if y equals f of x, then f inverse of y equals x. So it just interchanges the inputs and outputs. And sorry, the notation there should be a little -1 superscript. So that is not an exponent. That is just a shorthand for f inverse, okay? All right. So they undo each other. So the way we know that two functions are inverses of one another is if we compose them and we're just left with the input. So if f of g of x equals x, and if g of f of x equals x, then we would consider g to be the inverse function of f and f to be the inverse function of g. All right? And we would notate that once again with a little superscript of -1. That is not an exponent. It's just shorthand for inverse. So f of f inverse of x equals x, and f inverse of f equals x. A more important note is that the domain of f must be equal to the range of f inverse, and the range of f must equal the domain of f inverse. Okay, so since they swap inputs and outputs, they swap domains and ranges. All right, so in this first example, we're given a function, f of x equals 4x, and I want to think of a function that might be its inverses, or its inverse. So this is called finding the inverse by inspection. There will also be a way to systematically find it. But I want you to just think about what could we plug in for x in this function that would just leave us with x after we plugged it in. Well, this is 4 times x, and I know that 4 times 1/4 is 1, so I'm going to conjecture that the inverse function will be 1/4 x. So the way we're going to test that is by composing in both directions. So I'm going to start with f of f inverse of x. So this is f of 1/4 x. And so now I'm just replacing the x in f with 1/4 x. So I still have the 4, but that x gets placed with 1/4 x. Multiply that out, and we're just left with x. So in that direction, it worked. We're on the right track. All right, now let's try composing in the other direction. So now we're going to do f inverse of f of x. So that's going to be f inverse of our function f of x is 4x. So now we're replacing the x in our suspected inverse function with 4x. So that's 1/4 times 4x. Multiply it out, and we're just left with x. Okay, so this is the correct inverse function. All right, which of the functions is the inverse function of f of x equals 5 over x minus 2? So we're given two functions. We want to know which is the inverse. So let's start with g of x. And I'm just going to compose f of g of x, which is f of x minus 2 over 5. All right, so I'm going into my function f. I'm replacing this x with x minus 2 over 5. So that's going to be 5 over x minus 2 over 5 minus 2. All right, well, this is a big mess. Let's see, it could simplify down. To be able to combine the fraction in the denominator, I'm going to put that 2 over 1. And then we're going to get a common denominator of 5. So 5 over 5. All right, so now we have 5 over x minus 2 minus 10 over 5. Let's see, what's that? Whoops. 5 over x minus 12 over 5. Divide by a fraction, I'm going to flip and multiply. So this is going to be 5 times 5 over x minus 12, which is 25 over x minus 12. This is not getting any simpler. And at this point, this clearly does not simplify down to just x. So we can definitely say that g is not the inverse of f. So it says which one is, so let's hope that h is. All right, so let's check h. So if I do f of h of x, that's f of 5 over x plus 2. Okay, again, I'm going in and I'm replacing this x in f with 5 over x plus 2. So I have 5 over x plus 2 minus 2. Okay, that's 5 over, those 2's are going to cancel, so that's just 5 over x. To divide two fractions, I'm going to take the bottom one, flip it, and multiply, so that's 5 times x over 5. Our 5's cancel, and I'm just left with x. So it worked out in that direction. We do have to test it in the other direction, so now I'm going to do h of f of x. So that's h of 5 over x minus 2. So now I'm going into h. I'm going to replace this x here with that 5 over x minus 2. So 5 over, instead of x, it's 5 over x minus 2, and then plus 2. Okay, again, I have a complex fraction here. So we just take the bottom fraction, flip it, and multiply. So this is going to be 5 from the numerator. You can put it over 1 if you like. Times, flip the bottom one. So now x minus 2 over 5 plus 2. Okay, these 5's cancel. I'm just left with x minus 2. So x minus 2 plus 2. 2's cancel. And we're just left with x. So it worked in that direction, and now we've verified that, in fact, h of x is the inverse function of f. Okay, so the consequence graphically for inverse functions, since they swap inputs and outputs, is all of the coordinates are essentially inverted, right? So if AB is on the original function, then BA is on the inverse function. So by kind of transposing every single coordinate pair, we get a reflection over the line y equals x, okay? All right, so let's take a look at this graphically. So I'm going to verify that these two functions, f and g, are inverse functions of each other graphically. These are both just lines, so this shouldn't be too difficult. To graph a line, we really just need 2 points, right? And then we can draw a straight line through those 2 points. Now, how accurate I can make this freehand is another question, but since the domain of any linear function is all real numbers, I'm just going to choose an x value to plug into the first one. So I'm going to say f of 0. Note that f of 0, if I plug that in, I got 2 times 0 minus 3, which is negative 3. So that's the coordinate 0, negative 3. So I'll plug that in on my graph, 1, 2, 3. And then let's just choose f of 1. So now that's 2 times 1 minus 3, which is negative 1. So that's the point. 1, negative 1. So 1, negative 1. All right. My line is something like that. Okay, so then for g, what I'm going to do is take the y values of those corresponding points and plug them in. So if I do g of negative 3, for example, that's 1/2 times negative 3 plus 3, which is 1/2 times 0, which is 0. Okay, well, notice that that gives me the point negative 3, 0. Swapped input and output. So left 1, 2, 3, and 0. Now I'm going to plug in the negative 1. So that's 1/2 negative 1 plus 3. So that's 1/2 of 2, which is 1. So again, negative 1, 1. Swapped the x and the y. So something like that. Connect the dots. Like that. And again, this is freehand, so not super accurate, but that's a reflection essentially over that line y equals x. Okay, because of that graphical consequence, the reflection over the line y equals x, only certain functions will have expressed inverses without doing something like restricting the domain. So those functions have a property called one-to-oneness. And a function is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. So x doesn't cheat on y and y doesn't cheat on x in both cases. And so we do have a visual test for that. It's called the horizontal line test. So a function is one-to-one if you can draw a horizontal line anywhere and it'll only hit the function at one point. It is not one-to-one if you can draw a horizontal line at some point and it'll hit more than 1 point. So this parabola down here is not one-to-one. But the cubic up here is one-to-one. So just to give you some more reasoning on that, it's because if we do a reflection of a parabola across the line y equals x, you're going to end up with a situation that looks like this. And we know that's not a function because it doesn't pass the vertical line test. So for a function to have an inverse, it must be one-to-one. Graphically, it must pass the horizontal line test. Okay, let's talk about how to systematically find the inverse of a function algebraically, because doing it by inspection only works for very, very simple functions. So first thing you want to do is decide if the function is one-to-one. So you can graph that in Desmos and use the horizontal line test. All right. If the equation is written in function notation, we're going to replace f of x with y. So over here, I have a little example. So replace f of x with y. Then we're going to interchange the roles of x and y. So everywhere there was a y, we're going to replace it with x. Everywhere there was an x, we're going to replace it with y. And then we're going to solve for y. Okay? So you want to get y isolated again. And finally, when you do that, you're going to replace y with f inverse in the new equation. Now, I will say that this is a parabola over here, so this is not one-to-one. And you'll note that you actually get two solutions because of that, right? You get plus or minus root x minus 1. So we would have to restrict the domain on that to only be a piece of the parabola, the original parabola, before we could actually define an inverse. So what I mean by that is we could just look at, say, the right branch of the parabola. So if I go in and get rid of the left branch here, now it's one-to-one. And now I could define an inverse, which would maybe be just the positive square root, okay? But let's try this. We're going to try this with this function, 5 minus x over 3x plus 2. I will tell you, you can graph this in Desmos if you want to see. It's a hyperbola, but it is one-to-one. Okay, it passes the horizontal line test. So let's start by replacing f of x with y. Okay. All right, everywhere there is an x, we're going to replace it with y, and we're going to replace the y on the left with x. So this is going to be x equals 5 minus y over 3y plus 2. Okay. And now we're going to try and isolate y. I picked this example because this is one that students tend to struggle with. Note that there are two y's here, and we need to isolate it as a single y. So I'm going to show you how to do that real quick. We're going to start by making this not rational anymore, and we do that by multiplying both sides by the denominator. Okay. So on the right-hand side, that's canceling my denominator. And I can distribute the x on the left. All right, so we're going to get 3xy plus 2x equals 5 minus y. All right, so note that I still have two y terms. So here's the key. You want to get all the y terms on the left-hand side. Anything that doesn't have a y term, we're going to move to the right-hand side. So that's going to involve adding that y on the right over here, so 3x y plus y, and subtracting that 2x on the left. So that's going to equal 5 minus 2x. So we still have two terms with y in it, but now that's a common factor. So we can actually factor out the y on the left. So I'm going to factor out a y. Let's move up here. Factor out a y. I'd be left with 3x plus 1 equals 5 minus 2x. And then the last step is just divide out what's in front of y. So I'm going to divide both sides by 3x plus 1. Okay. We're left with y equals 5 minus 2x over 3x plus 1. Perfect. Last step is to notate in inverse notation. So f inverse of x is equal to 5 minus 2x over 3x plus 1. Okay, one more example. Okay, we're going to find the inverse of f of x equals the square root of 2x minus 3. I do want to mention domain and range on this one because we're dealing with a square root here. So in this class, we're only going to be looking at real number outputs. We'll never look at imaginary outputs. So when we have a square root, that's what defines imaginary outputs, right? Is the square root of a negative number. We want to make sure whatever's underneath that square root, which is 2x minus 3, has to be greater than or equal to 0. It can be equal to 0, right? The square root of 0 is still 0. It just can't be negative. So if I want to figure out my domain, I'm going to solve this inequality, which is pretty straightforward. 2x is greater than or equal to 3. X is greater than or equal to 3 halves. So my domain in interval notation is just from 3 halves to infinity. My range, thinking about the range, well, the smallest my output can ever be is 0. And then this is only going to output positive numbers because it's a positive square root. So my range is 0 to infinity. Great. Let's go ahead and find the inverse. This one's actually quite a bit easier than the last one. So y equals root 2x minus 3. Swap x and y. X equals root 2y minus 3. Okay, now we're going on to try and isolate y. Let's go ahead and square both sides. So now I have x squared equals 2y minus 3. Add 3 to both sides, so x squared plus 3 equals 2y. Divide out the 2. Y equals, I'm just going to, dividing by 2 is the same as multiplying by 1/2, so 1/2 x squared plus 3 halves. And then write it in inverse notation, so f inverse of x is 1/2 x squared plus 3 halves. So note that this is a parabola, but it's actually not going to be the whole parabola because my domain for this is going to be the range of my original function. So the domain is only going to be 0 to infinity. So that's only going to graph the right branch of the parabola. And my range for this is the domain of the original one. So the range is going to be from 3 halves to infinity. And you can go graph that in Desmos if you know how to restrict the domain. If you don't, I can definitely show you when I get back. That's it. All right. You're going to go ahead and get started on your group work and the delta math.